for airports. And one of the projects that we're doing is Project 244. It's an environmental project which is looking at how we can make improvements to modeling helicopter noise. Juliet Page is the principal investigator of this ongoing research. And what I want to do is turn it over to Juliet. She's going to have a presentation and then open it up for some questions and comments at the end of the presentation. So take it away, Juliet.
Okay, thank you, Joe. Welcome, everybody. I appreciate you taking time out of your busy schedule to call and dial in and hook up through the internet to this presentation today. So, as Joe mentioned, this is an airport cooperative research program. We're developing recommendations for helicopter and tiltrotor noise modeling. And the structure of today, I'm going to spend about 40-45 minutes or so just kind of going over a high-level overview of the project and our recommendations. And at the end, I hope we'll have 15 minutes or so to have a little bit of discussion or clarification of questions that you might have. As Joe mentioned earlier, it would be beneficial if everybody who is on the line is able to mute their phone so that we don't have a lot of extraneous background noise making it difficult for the participants to hear. And I will open up for questions at the end. Okay, so first thing to note, I'm with the Volpe Research Center, the U.S. Department of Transportation. My email address and my phone number are showing on the screen now. I've recently moved to Volpe from my prior position at Wiley. So those of you that know me, I do have the new contact information. I'm gathering most of you did email directly or you had emails forwarded, so hopefully you have it. There is an accompanying white paper that describes with all of the technical guts of our recommendations and the rationale behind that. And I will encourage everybody to review that if time permits, and hopefully you'll be able to have time to go through that, or folks in your organization that have an interest in helicopter noise modeling. And we are seeking feedback on that through the end of May, through May 28th. And that, we'll take all of the feedback and adapt accordingly. So the most efficient way is to send feedback via my email address or anyone on my team, and you'll see their emails show up shortly. They're also, everybody's listed on the white paper. If you do not have a copy of the white paper, feel free to send me an email and I will get that out to you after the webinar. Okay, so, all right, let's carry on here. So the objectives of this project was, there's three basic goals. One, we wanted to review, evaluate, and document what noise models are already out there in existence and being used. We wanted to identify improvements to INM or AEDT, which is the US FAA models for analysis, and to better capture helicopter and unique aspects of tiltrotor operations. So we did a pretty comprehensive look at all of the modeling limitations within INM and AEDT, and we're in the process of developing a supplemental document to provide guidance for modeling that. The white paper is not the supplemental document. The white paper is a listing of our recommendations and the rationale. Once we're through this feedback process and have gathered input from many of you on the line and others who aren't able to join us today, we will be putting together that document, and that will be one of the final deliverables on this project, which will then hopefully be poised to enter into the regulatory process, the standards review process for review, any further updating, and eventual balloting. The long-term goal is that with an updated standards document, approved document that has improved modeling recommendations, that will then provide the impetus to update AEDT in the U.S. and hopefully will also provide some suggestions and recommendations for other noise models in the EU and in other places around the world that can then be updated accordingly. So The motivation statement on this slide I won't read, but that's kind of the motivation behind this project. So that said, what we're looking at here is the modeling aspect. We're not making any judgments as to which is the right metrics to use to capture annoyance, or which is the right community noise metric to use to address helicopter and tilt rotor noise. Our impetus is to focus on the physics and the modeling so that you can capture the right information, that the metrics can be computed accurately. After that, the outside of the scope of this project is what's the right metric to use for helicopter and tilt rotor community noise. That's not within the scope of this. I just wanted to say that up front. Okay, so here's the project team for our ACRP funded project. We have Volpe on I'm the principal investigator leading this effort. Eric Boker, David Sensig at Volpe are on the team as well. Wiley is the prime contractor for the project. Kevin Bradley at Wiley is the project manager, and we also have involved Ben May and Chris Hobbs. NLR in the Netherlands is on our team. Harry Brower is the lead there, and Martin Kniestra has also been very helpful in this project. And Clint Morrow is the lead at KB Environmental Sciences, and he's also providing a lot of valuable input from the community modeling aspect. So slide 4, we have a list of our panel members. So those of you not familiar with ACRP projects, every project has a group of panel members that help oversee and guide the project from before the project even starts all the way through the end. So they provide a lot of valuable technical insight, direction. They've also helped me identify many of you on the phone that I should be reaching out to that can hopefully provide some instructive feedback on this project. So we'd just like to acknowledge the panel members as well. So the outreach objectives. So this is the particular task that we're working on right now. So as I mentioned, we've developed a white paper that lays out our modeling recommendations for helicopter and tilt rotor noise, and that is available. Email me if you don't have a copy, and I'll be happy to send it to you. It basically goes through the technical rationale as to why we're making specific recommendations, and we are looking for feedback on those recommendations, be it good, be it bad, did we miss something, should we consider things that we may not have mentioned in there, or what have you. We're looking for any recommendations or feedback you may have through 28th of May, and that's so that we can maintain our project schedule. So that's about a month from now. Once we receive that feedback, we will modify, adapt, take it into consideration, adjust the recommendations, add ancillary recommendations if needed, and we're going to incorporate this into a document that will then go into the SAE, ICAO, and potentially other standard review processes. So feedback can be provided to myself or any of our team members. So today, for the webinar, what I'm going to go through is a very quick literature review to try to set the framework of the first task we had, which was looking at the noise models that are out there. And then we're going to go through our 7 key modeling recommendations, and we'll have time at the end for Q&A and discussion. So just to follow up from the beginning entry remarks, those folks who are joining late, please put your phone on mute. I will be briefing until for 40 minutes or so, and then we will have some time for open discussion at the end. So those of you that are not on mute, please do so to cut down on background noise. Okay, so back to the models that are out there. So there's a wide spectrum of models. I'm kind of using air quotes here around the word models. Everything from very simple operational guidance in the form of, the graphics from the Fly Neighborly. I mean, that in and of itself is a particular model for helicopter noise. All the way through integrated models, simulation models, then there's first principles calculation methods that utilize a combination of computational aeroacoustics and dynamics models together with one another. And those are very more complex, have a lot of input burden in terms of what information you need to even run the models. And so there's this wide spectrum of models that are out there. They all have their pros and cons and varying degrees of accuracy and user input burden. And so in this project, we reviewed all of those. And since we're targeting AEDT, the integrated noise model, sort of in the middle, that community noise modeler can use, and community noise modeler can have access to the data to use. Some of the higher fidelity models are very good for assessing if you improve this or you add this feature, what does that do to your answer? So anyway, so let me just step through them quickly. So as I mentioned, this is straight out of the Fly Neighborly Fly Higher chart, and it is a model. It's a very simple model where you look at your height above the ground and whether you're a small or large helicopter, and there you get your noise level out. Very simple, very easy to use, and a lot of people use this as very valuable. Stepping up a little more complex, you can account for the BVI, and the HAI Fly Neighborly program also provides information to the pilots so that they can start to understand some of the noise source emission and can be aware of the community noise aspects. Then we get to the integrated noise models. INM, which I'm sure many of you have been using over the years, as well as AEDT, which is the current FAA model. INM will be sunsetting in the future, so everything will be moving to AEDT. But that's an integrated model, and that in there it has a GUI with it, and the user can define the operations, select the vehicles. It comes with a built-in database, and there are some limitations to the fidelity of the source, the modeling, and the operational modes within that model. And this is where the crux of our recommendations are targeting. So what particular aspects of AEDT can be improved in the future to have a better, more accurate noise results coming out. So those of you on the line, please hit me. There'll be an opportunity towards the end for Q&A. So here's some of the limitations of INM and AEDT, which you guys are probably fairly aware. It doesn't handle tilt rotor operations. You can sort of trick it to do them. It ain't pretty, but you can get some answers out. But as well as on the helicopter side, there's limitations on the directivity of the model. So you can have a left to center and a right directivity. There's built-in spectral classes. And there's a finite number of just a couple of different operational modes which have specific noise data with it. So moving on to the next layer fidelity model, you get into simulation models. The Rotorcraft noise model, advanced acoustic model at Wiley is an example of those. And I was instrumental in the development of those for many years before I went to Volpe. So these have as their core noise spheres, and you have one noise sphere that represents the spectral emission 3D for every single type of flight operation or flight condition. You can also handle stuff like maneuvering and other aspects which are a little more complex than what is currently in AEDT. There's also HELENA, which is an EU model. There's a lot of similarities between HELENA and Rotorcraft noise model and AAM in the US. They are both simulation, time-based simulation. They can utilize, HELENA can utilize noise spheres as well as it has ability to handle noise carpets as well. And NLR in our team is one of the supporters or co-developers of the HELENA model. Now, stepping now to a little more complex process, there are tools like TRAC, the Tiltrotor Aeroacoustic Code, which is a NASA tool that is a hybrid code that uses computational structural dynamics along with computational fluid dynamics, and it has the the capabilities coupled together. To utilize these type of models, you need a lot of information about all the blades and the airfoil shapes and the blade dynamics and properties, and you know, there's a whole lot of information you need to be able to utilize these types of models. And they're great for research and for analysis and other things, but it's way more data than your typical community noise modeler that's, you know, doing some sort of a NEPA assessment at a heliport or an airport or some other location. But these are very instructive for development of data and understanding the high fidelity physics. So they work by generally, you start with the rotor aerodynamics and the performance, and then they're coupled together, and you extract the time varying pressure, use a Folks-Williams-Hawking solver like a WAP-WAP or PSU WAP-WAP or an ANOP. Has the formulation of Frank Faraset's formulation in there. And from there you can obtain the source characteristics, either propagate it straight down to the ground, extract a noise sphere, what have you. And then these higher fidelity models can be used analytically to generate noise source characteristics that can then be used in the lower fidelity models as well. CHARM is another example of a high fidelity tool. This one is developed by Continuum Dynamics in New Jersey, and it also has a capability of doing the aerodynamic and the blade structural dynamics, and from there extracting the noise characteristics. You can propagate straight down to the ground or feed them into a propagation model that takes into account additional, you know, atmospheric and intervening environmental parameters for the propagation. So there are many others out there. I just, you know, picked a few to show you. CHARM has the ability to also handle multiple rotor systems and other kind of cool looking crazy vehicles. So, as I mentioned all along, there's varying degrees of fidelity, accuracy, and capabilities of the models that are out there. And you know, we're targeting community noise modeling. So again, a lot of these models, it's good to understand them. It's good if you have access to them, if you need to develop databases or you have a limited empirical database and you want to augment that with some analytical stuff in between. Now I'm going to move on to our recommendations. And I have 7 slides for each of the key recommendations, and I'll go through each one of them in order. So these are the metrics that we are recommending that the model should be capable of computing. In today's AEDT and INM, all of them with the exception of the last one is already included. The last one can be computed via post-processing from INM and AEDT. So this is not really much of a change in the status quo. And on this slide, I'd be interested in hearing from you all if you think there are any key metrics that are missing here. I recognize that there's a lot of other research going on today looking at the community acceptance side, which is the right metric to use, and so on and so forth. And we're not saying which one is the best one, which one should be used. We're trying to make sure that the model is capable of calculating the ones that are either in use today or will might likely be bubbling to the surface, shall we say, you know, given the current and ongoing research in the community noise area. So that's the list, and like I said, I'd be happy to hear if we've missed any, or are there any additions that should be made, or what have you. Okay, moving on to the next priority here was spectral content. So the current model of INM starts at 63 hertz and goes up from there. And as you're all likely well aware, the fundamental noise for helicopters is generally below 63 hertz. There can be some significant differences in the computations. if you do not include the fundamental and the first few harmonics of the rotor fundamental, when you're computing C-weighted, unweighted, metrics like D prime, which is an audibility metric that occasionally is used for Grand Canyon and National Park studies. So there can be significant differences. So that is the genesis for our recommendation that spectral content be included in the model down to and including 10 hertz, 1/3 octave band. Here's an illustration of, for those of you that may not be fully plugged into the A and C weighting details, but on the lower left here, I'm not sure if you can see the pointer, but this is the C weighting curve, and this is essentially the weighting that gets applied to each frequency, and then the noise gets integrated across all bands. A weighting drops off significantly at the low frequencies. A weighting is essentially a capture of the human ear and human hearing, and we don't hear a whole lot of the low frequencies. Whereas C weighting is often used to determine vibration and structural response for buildings and things like that, and they do respond well to low frequency noise. So it's fairly flat all the way down, well below 50 hertz, and then it starts to roll off. So all of this energy in the purple area is not currently included in the C computations in INN. The current version of AEDT does have inclusion of capability to go down to 10 hertz. The databases are going to need to be expanded, though. On the right-hand side, I'm just showing an example of a spectra for the Bell 412 and the Canadian Forces CH-146 vehicle that was measured at Moose Jaw. This is publicly available data with the Rotorcraft noise model, and from there you can see, the peak noise is the fundamental for low speed and high speed is well below 50 hertz. Okay, moving on to the next recommendation. This is flight path angle. So we recommend that it's necessary to include the effects of approach flight path angle on source noise characteristics. So, as I'm sure I'm preaching to the choir here, BVI on approach is a major noise emission condition, and helicopters generally on 6 degrees approach, they're at maximum BVI. Obviously, there's configurational differences and operational differences, but generally there's a peak around 6 degrees. If a pilot flies a low noise approach at 3 degrees or 9 degrees, they're off the BVI maximum, and their noise source emission, looking at the source characteristics, is lower. The way the model is currently structured, the ADT and INM model is currently structured, it has one set of approach noise characteristics per vehicle. So if you are attempting to model a low noise approach or design a low noise approach for your facility that will reduce the noise on the community or reduce the contour size in a particular area, you're never going to be able to see the benefit of that in the model the way it is currently structured. So that's the primary rationale behind a recommendation that you need to include approach flight path angle source characteristic variability within the model. Otherwise, you're kind of throwing the baby out with the bathwater, so to speak. The graphics here are just an example of the noise spheres for 3 degrees on the left, 6 in the center, and 9 degrees on the right. And you can, they're all plotted to the same. This is dBA over, dBA levels. You can see the 6 degrees obviously louder than the other ones, and that's due to BVI. Okay, we also feel that it's important to include the spectral characteristics along with your approach noise. So the current implementation in AEDT is to have a single spectral class for approach, one for departure, and one for level flyover. Because the BVI noise versus the non-BVI conditions can have dramatically different spectral characteristics, it's important that you permit the spectra to change and not just the overall level to change as a function of flight path angle. Those are just some cool photos of BVI, what it is, when it occurs, and why. I'm not going to get into a whole lot of detail on that here. We don't have hours and hours to go through BVI noise, but there are conditions, different loading, flight path angle, drag or thrust state of the vehicle that can affect the relative angle between the rotor wake and the blades, which will impact BVI or not. So it can be condition specific as well as vehicle specific. And it's important to be able to capture that adequately. Okay, moving on to the next highest priority item is lateral directivity. So the noise emission from helicopters is fairly complex. It is not symmetric like fixed-wing aircraft. The current AEDT and INM models were developed to have a limited amount of lateral directivity. They recognized that the right, the center, and the left are different for helicopters. So it has essentially 3 lateral directivity points. Center line, directly under track the vehicle, right and left, which are defined at a 45-degree emission angle. If we look at the higher fidelity noise source emission of vehicles, the peak may not necessarily be at 45 degrees, and there is often noise emission that is at higher angles heading up the side of the, if you picture the sphere heading up towards the rotor plane. You know, if you're flying above uniform flat Earth, those probably aren't a big deal, but once you start to bank the helicopter or try to do an analysis where you may have terrain or helicopters flying below the height of nearby canyons or other features, you've again missed a lot of the noise characteristics. And we feel it's important that the model do have a more lateral directivity fidelity in it. So here's just a few examples. We did, one of the analysis we did was take the high fidelity empirical noise spheres, essentially decimate them, lower and lower fidelity, and assess what the impact was on the contours and integrated noise metrics, and use that to quantify some of the differences of including it versus not including it. And a lot of the details of this is laid out in the white paper. Right now I'm just going to give you a pretty high-level overview. So this next slide here, I'm showing A-weighted levels across a lateral. Picture a bunch of microphones set out laterally. The helicopter is flying out of the page towards you, so the starboard side of the vehicle is on the left side of the graphic, and the port is on the right side of the graphic. And if we take these decimated noise spheres, the one with the blue labeled full resolution is if we use the high fidelity measurement data. This is the A-weighted level across the flight track. He's at a height of 1,500 feet. So, you know, 1,500 feet would be the 45-degree point, which is like the right, or excuse me, the left. This is the port side. The left in INM or AEDT. And all this other data is reaching the community. It's coming from points beyond that, which, you know, you're able to capture in the full resolution. If you decimate it down further, you can see what some of the impacts are. So you can have a single event dBA level, you know, off by, you know, upwards of 7 dB, just by neglecting to include some of the lateral directivity effects. And again, this is just one example, one flight condition, one particular thing. There's some more examples of this in the white paper. But this is the genesis for that specific recommendation. that one needs to include higher fidelity lateral directivity in the model to more accurately capture the noise. Here's an example of higher speed where the advancing side has got more of the noise, and again, you know, it's pretty significant differences between using a high fidelity versus a right, center, left sphere, and we looked at other varying degrees in between. So there are implications to this lateral directivity modeling recommendation. Our suggestion is that we leave it up to the manufacturer to define what angles need to be prescribed. That is going to be very vehicle and condition specific, and the manufacturers probably have, you know, modeling that they've done in-house to better ascertain this. We think that the criteria for saying how many lateral directivity positions or angles need to be defined should be parallel to some of the current FAR 36 language that specifies, you know, how different things can be between the lateral microphones to capture the maximum. So there's probably some current language out there that could be woven into this lateral directivity recommendation. And if anybody has suggestions, we welcome your input on that. For level overflights, left, center, right might be okay, but the peak might not be at 45 degrees. So rather than just having the finite left, center, right at 45 degrees, say, okay, here's the left, here's the center, here's the right, and specify what the angle is. We've had some preliminary discussions with the AEDT developers about what that would require in terms of modifying the tool to handle N angular locations, and the NPD metrics would then be at each of the N angles, and possibly have, you know, an N maximum or something like that. So imparting it into the tool of AEDT is, you know, straightforward programming, and I do recognize that getting the data to provide this for AEDT to include in the database is a bigger deal. And we can talk a little bit more about that later. You know, there are practical implications now on, like I just mentioned, on where you get the data. Historically, NPDs have come from some of the FAR 36 measurements, although manufacturers often augment that data and provide supplemental information to the FAA for inclusion in AEDT that is not necessarily directly from the FAR 36 certification flights themselves. And I recognize there is a cost impact to that, especially for some of the smaller vehicles that are using simplified certification procedures. So we are looking also for feedback on that. There's a historical database, historical data in the AEDT database, including for some vehicles that may not even be flying now. So it's not like you're going to get to go out and do a flight test program to do that. Somehow they're going to need to be expanded. Personally, I think that a blend of analytical with empirical modeling can go a great way in expanding the current data set without requiring flight tests and measurements and things of that nature. You know, started out with reviewing some of the higher fidelity models, and I think that one can utilize those capabilities in conjunction with the existing database to expand it. There's possible proprietary concerns that some may have over an expanded amount of detail going into you know, an FAA database. I'd like to hear if you have concerns over that and what they are. And then on the military side, you know, we have to remember that AEDT also has a full set of military vehicles in it for mixed-use facilities. So there are potentially some security issues over military helicopter data as well. So again, if folks have thoughts on that, we welcome your input. Okay, the next recommendation, and this is a little bit of a softer recommendation, is that the model should be structured so that it can handle maneuvering flight. There's a couple of different categories of maneuvering flight here. So one of the pieces we feel it's important that a community noise model capture is the ability to model optimized low noise profiles. So for example, if you have a drag device that you're putting on there, like Fred Schmitz's X-Force, you can avoid BVI. Or if you were, have some other vehicle things coming down, designs that will take into account different drag states or what have you, that you can actually include the source characteristic modification. Now, that's not to say that the database needs to include all of these things, but you need to give the user the capability that if they're attempting to model a scenario at a particular vertiport or airport, and they know that this vehicle will be in use, that they have the ability with their own customized data or whatnot to be able to model that in the tool. In the way it's currently structured, that's very difficult, if not impossible to do. There's also cases where LMAX and other non-integrated metrics need to be predicted on a high fidelity mesh. If one is got complaint data or what have you, or you're trying to use a community noise model to do some more high fidelity analysis to understand something in a particular area near an airport or a heliport. LMAX and other non-integrated metrics can have a large variation, more so than DNL or SEL will. There's also situations where time above metrics are to be computed. For example, in the parks area, in national parks, when you have vehicle strong changes in operational state, turn entries, pull-ups, pushovers, and you have significant maneuver time durations, you can get some increases in the time above metrics. Again, I think this is a lower priority, but I think it's important that the model be structured so that those types of features can be included in the future. There's also environmental conditions that can impact the source characteristics. If you have a 5,000-pound helicopter operating at sea level versus operating, at Denver at 5,000 feet, you have a different noise source characteristic, and the model should be able to include that. Now, this is an area of active research, looking at maneuvering flight and the source characteristics, and a very high fidelity physics research is going on in this area with a number of sponsors, including Army, NASA, and others. And I recognize there's going to be a lot of information coming out this way. So our recommendation here is low on the priority list, but I think it's important to acknowledge that this research is likely to yield some simplified methodologies that could be included in an AEDT community noise model. Okay, and finally, tilt rotors. So tilt roters were not the focus of this, but we did want to give them some due diligence and address the tilt rotor configuration here. So one of the things we did was to try to run a tilt rotor analysis using the existing INM. So how can you trick INM into running a tilt rotor? And you can see the effects of that, us doing gymnastics to run tilt rotors in INM in the full white paper. And obviously there's a lot of challenges to do that, a lot of tricks where you're running separate segments and you're adding grids to get the overall answer, which is, not slick. It sort of works, but there are certain aspects limitations that it has. So you know, there's, with the hopeful future introduction of tilt rotors into the commercial arena, the model needs to be able to handle tilt rotors. So there are different flight modes, including transition, which just don't exist for fixed-wing helicopters. And that associated with that, the movements and the associated noise source database needs to go with that. So we've identified several of the modes of tilt rotors that need to be handled: hover, takeoff, flight, transition, and different types of flight modes. They each need to have their corresponding spectral class and noise source characteristic information. So specifically, you've got helicopter mode, you've got an airplane flight mode, and then you have the transition in between. And the model needs to, you know, have the user be able to define operations using, you know, those pieces. And one last piece that we looked at was the propagation modeling. We didn't delve into this in much detail other than to acknowledge other research that had been done recently. The references at the bottom, detailed weather and terrain analysis for aircraft noise modeling. All of that essentially applies to modeling helicopters and tilt rotors for community noise. We've already addressed some of the lower frequency recommendations up above. So for this particular project, we're essentially saying, yeah, all of these other recommendations of improvements in atmospheric absorption, layered atmospheres, being able to handle intervening terrain, and the next step after that going to curve rays with more diffraction capability. Those are equally applicable to helicopters and tilt rotors as well as fixed wing. So those are our key recommendations, and here's the last page. I'll leave this sitting up for a while. We're looking for feedback by the 28th of May, and there's a contact for myself, Kevin Bradley at Wiley, Harry at NLR, and earlier on and in the white paper we have ways to reach out to all of us. So at this point I would like to open up for some discussion or burning questions you all might have.
Well, Juliet, this is Ricarda.
Oh, hello.
Hi. You did a great job.
Thank you.
It's a little overwhelming. A lot of the suggestions are really right on point, like the low frequency, and also the ability to change the flight angle, the slope. I think that's really important.
Okay, thank you.
Hey, Juliet. This is Ben.
Oh, Ben Sim. How are you?
Hey, do you care about the low frequency noise vibrating buildings and windows?
In so much,
care about BGI?
Well, okay, so in so much as it is if you look at some of the subjective human response, noise is not purely just acoustic, but just what comes in through your ear. There's also a vibration component to annoyance. So I think that the low frequency needs to be captured if the metrics are to recognize that. I have also seen instances where the noise models have been used to compute sea-weighted contours in areas where there are historical structures or other buildings where they're worried about vibration, and so they may use a noise model to compute sea-weighted contours that are then used in conjunction with other tools for that.
Hey Juliet, this is Mike Watts. How you doing?
Yeah.
So when you're considering the number of microphones, I think that also, you know, there's the big controversy on whether the 4-foot tripod mics, which is what's used now, or the ground mics, or even the elevated mics on towers. So I think that is a key component that has to be specified when you're specifying the number of mics.
So I think to address that, there are different ways you can interpret that. Our recommendation is that the model include the lateral directivity of the source characteristics in such a way that it can capture that. You can decouple the model from how you gather the empirical measurements. And I totally agree with you that if you're measuring on a ground board versus 4-foot high microphone versus, something way high up, it impacts how you would process and interpret the data to capture what is the noise source emission of the vehicle. And yeah, we've had lots of discussions about that over the years. But I think for the purposes of the recommendations we're putting together here, we're recommending what the model should include, not necessarily how you get that data to input to the model. So I'm trying to avoid that can of worms if I can.
Okay, it seemed like you were just touching on it with the number of mics thing, so.
Yeah, they're definitely related. They're definitely related, but the purpose of this is not to say how you should go out and do your measurements. The purpose of this is what should be in the model to when you're using it to do analysis to capture the right results. So I'm deliberately trying to decouple those as best I can. Now maybe we can't, and maybe we need to, let that Pandora's box lid crack open. I'm not quite sure how one would go about doing that. But if you have, further details on that, please, or recommendations or input, please provide that to me. I'd welcome it.
In one of the slides, it seems like you were letting the manufacturer define the directivity the effects, and that implies the number of mics. But it also, what's the oversight if we all will play the game of what's the best for our aircraft. What's the oversight by the FAA when they get these directivity effects? Be okay, show me the data that you got this from, so I can make sure that you captured the correct directivity effects, or is it going to be just okay, this is what you say it is, we'll believe you.
Right. So I hear you on that. So my suggestion there is to word the criteria in a way that's parallel to the FAR 36 language. And forgive me, I don't remember the wording, but if you look for fixed-wing aircraft in FAR 36, and they have a series of lateral microphones that have to capture the peak for a departure. There is language in there that specifies how many you need and where you need to put them to ensure that you've really caught the peak and you haven't just placed it so that you're missing it and fudging it, in layman's terms. So there would need to be some language similar to that that would ensure you've defined it in such a way that one can't play games.
Okay.
That's kind of what my second dash there is aiming at, although I didn't probably word it as well as I could have.
Juliet, this is Eric Jacobs. So you're really talking about an expansion of FAR 36?
No, I'm not talking about expanding FAR 36. I'm talking about making modeling recommendations, but the language that goes in the modeling recommendations might parallel some language that's already existing in FAR 36.
Okay. Also, the question so far, everything that you've been talking about is constant airspeed conditions only?
No, the maneuvering is attempting to address the non-constant airspeed, so accelerations and decelerations
Okay.
and other type of maneuvers. Again, I'm not really sure how far down that rabbit hole we should go with this first set of recommendations. You know, my pragmatic side says, let's touch on it, let's lay a framework that maneuvering flight can be considered, so that some of these effects can be considered, but maybe not prescribe it in nth detail, because that is currently active research, and I think the jury's still out on where and how far you need to go on that. I think we're probably a little premature to pin that stuff down. At least that's my personal opinion on that. Unless, you know, obviously you guys have probably thought a lot more about that than I have. So if you have any suggestions on a way we can set the stage so that, you know, if the FAA funds improvements to AEDT to better capture helicopter noise, that, you know, we've got the hooks in the model there to anticipate improvements in the future.
Okay, it just particularly deceleration and acceleration, look at it being, if it's not in there, a big hole relative to actual use. So.
Yeah, some of the white paper we talked about that we've got the QSAM technique in the Rotorcraft noise model, which to a first order looks at the functional equivalence between flight path angle and acceleration and deceleration. I think that level of technology is mature enough, and that's been around for 10 years at this point, that's mature enough to go into the model. Maybe some of the higher fidelity maneuvering stuff, we just set a placeholder for the future.
Okay, and that's a little, maybe confusing me a little bit with, you're discussing peak noise at 45 degrees, and what were you meaning by that?
Okay, so the current AEDT model has got the right, center, and the left. The right and the left are defined at 45 degrees. So it's not that that's where the peak is wherever it is, but the model may or may not capture it.
Okay, but the only flight condition where it's 45 degrees with those mics is actually level cruise, right? It's not for approach, right, or for takeoff.
I believe the right, center, left is in all modes in AEDT. Somebody correct me if I'm wrong on that.
It's in there, but it's not but the data that goes into that is not 45 degree data for approach or takeoff. Maybe for takeoff, depending on what the height over the mics are, but.
Well, then that might be an inconsistency between your understanding the model and the model documentation, and that's probably something you and I should follow up with some of the AEDT guys, because my understanding is within the model, it assumes the NPD that's in there is at 45 degrees, and it does a linear interpolation to the, you know, the point of interest or wherever it's propagating to get to anything other than 45 degrees, and it extrapolates a flat line outside of 45 degrees. And I don't believe that changes for approach or departure. I think it uses the same algorithm for all modes.
That was the input data, if you're going off of noise certification type data as inputs and, for aircraft. For helicopters, it's not at 45 degrees for those flight conditions.
Okay.
And if I had a question on the 3, 6, and 9 degree approaches, we were talking about generic spectral changes for 3 and 9, or versus 6, or how are you handling that?
Our recommendation is to have a different spectral class for everything. So it's rather
by helicopter or by approach angle?
by both.
Okay.
If you think that can be simplified for BVI and not BVI and only have 2, then, you know, maybe we could do that. But if you're going to the effort to change it, might as well make it one spectral class per NPD and be done with it.
Yeah, you're just going to get peak BVI at different flight, you know, approach conditions for different helicopters. So.
Yeah, I recognize that. So if you have your database, which is a function of flight path angle, you know, and your particular helicopter, say its peak BVI is at, you know, 4.5 degrees or something, or 4 degrees. If your NPD data reflects that, then you've captured it.
And all, you know, that data going in is at VY airspeed for all these approach conditions. Are you handling other airspeeds?
The current model has an airspeed noise correction, so it has a series of coefficients that are in the database. I think it's a polynomial that allows for change in noise as a function of airspeed.
For approach condition or
You know, I'd have to look. I'm not sure if it's for approach. I know it has it in there for level. But that's, I'm taking a note of that.
Hey, Julia?
Yes.
Yeah, this is Mike Watts again. One of the things we were just discussing is the more you open this up for different conditions, the more I think the consideration needs to be to widen tolerances for the data acquisition, because right now a manufacturer will go out there and be there for several days just to hit the window for that 1 or 2 runs to count. So it's I don't know what it should be done about it, but it's something to, an unintended consequences for widening the amount of data is you need to see what the impact is going to be on the testing methodology. So
In other words, finding it for that perfect day that falls within the FAR 36 requirements, the temp and wind speed and humidity and so forth, right?
Right, because they'll be out there for days just to hit that window. So
Okay.
Once you say, okay, I need 3 times as many test conditions, then they might be out there three times that amount of days, increasing costs and all that. So it's just something to consider.
Yeah, I agree with you.
On that point, if you widen up the environmental tolerances and get more data within some limits, you can't have sandstorms or something like that, I suspect. But if the models have adjustments in them that they make for environmental conditions, and those are reasonable estimates, then one ought to be able to reverse those estimates back into the field data to come up with your normalized set of data. If you can't do that, then the fudge factors for environment aren't very good.
I'm sorry, what is your name? I don't
I'm
recognize
sorry,
your voice.
this is Norm Dottie from Russell Acoustics.
Okay, thank you. Yeah, I agree with you, Norm. Again, though, to as much a degree as I can, I'm attempting to decouple how one gets the data with what data should be in the model.
I absolutely agree, and I think
I think that's a major can of worms. It's definitely not within the scope of my project and current funding. I can tell you that. It is something that we can, by all means, note or include or provide feedback or something in our recommendations so that it's not forgotten and shoved under the rug. I don't think we're going to solve that in this current project, again, because we're focusing on what needs to be in the model, not necessarily how you get the data for the model. But I get what you guys are saying, and I couldn't agree with you more.
my work is principally with small heliports, dealing with things just in the last mile or so. We do a lot of ground testing, rather use the published data, but often we will set up a series of monitors in an area and fly the make and model, ideally, in and out of the site along the different tracks a few times, and use that data sometimes to adjust published data to try and make the real world. Certainly changing flight conditions, accelerating, decelerating, circling, etc., maneuvering, in other words, is the real world.
Mm-hmm. Well, thank you. Appreciate that. And again, you know, I've attempted to capture your comments here in my scribbly notes, and as well as I can. I will encourage you all to follow up via email as well. Make it a little easier on me to try to capture this. So definitely, or if you have any thoughts that, you know, dawn on you in a day or a week from now, please feel free to reach out to us. So it's just 1 o'clock now. Is there any last... Yeah.
Juliet, before you leave, this is first Smith. I just have had to make that comment about the tilt rotors. There's a non-unique control problem here where you can actually optimize the approach of the tilt rotor, not just flight path, but the configuration itself, and how you take the load on the wing versus the rotor. So you have to be careful about that when you open this up. Just a comment.
Okay, so are you saying that within the tilt rotor modeling capability, it needs to have wing versus rotor loading as a parameter in the source characteristics database? Is that what you meant?
Yeah, that's it. When you look at it, there's a paper out there on this where we actually looked at it with theoretical experimental data. And there's a big difference. Also, the fixed speed of the rotor that you're trying to fly in this terminal space. So it's very tricky. It's like another layer on top of the normal helicopter approach, which I consider.
Okay. That's good input. Yes, I like it. Okay. Any other last minute saved rounds?
I'm good, thank you. It was
All right.
very useful.
Okay, well, I appreciate you all spending an hour online with me to hear me ramble on about this stuff. And like I say, please feel free to send me or any of the team an email with additional feedback or input. If you don't have the white paper, shoot me an email, I'll send it to you. And like we say, we're going to collect the stuff through the end of May. I got 2 weeks after that to get my final report together and through the system and out the door. So that's kind of a hard deadline at this point. So thank you all for participating. I really appreciate it. Thank you. Goodbye.
Bye.
Thank you.